What if I told you that two particles could be connected across the entire universe, instantly responding to each other's movements? This isn't science fiction. It's one of the most profound mysteries of quantum physics that troubled Einstein so deeply he called it spooky action at a distance. Welcome to the Einstein-Podolsky-Rosen Paradox, a thought experiment that began as a criticism of quantum mechanics but ended up revealing a universe far stranger than anyone had imagined. In the 1930s, quantum mechanics was revolutionizing physics but disturbing many scientists, including Albert Einstein. While acknowledging quantum theory's predictive successes, Einstein remained deeply troubled by its implications. He famously declared that God does not play dice with the universe, rejecting the fundamental randomness at quantum mechanics' core. Teaming up with colleagues Boris Podolsky and Nathan Rosen at Princeton's Institute for Advanced Study, Einstein devised what would become known as the EPR paradox, a thought experiment designed to show that quantum mechanics provided an incomplete description of reality. The EPR thought experiment begins with two particles that interact briefly and then move far apart, perhaps light years apart. According to quantum mechanics, these particles remain entangled. Their properties remain correlated no matter how great the separation. Imagine we measure the position of particle A. Quantum mechanics says we can instantly know the position of particle B without measuring it directly. Alternatively, if we measure the momentum of particle A, we instantly know the momentum of particle B. But here's the catch. According to Heisenberg's uncertainty principle, we can't simultaneously know both position and momentum with certainty. EPR argued that since we can predict either property with certainty without disturbing the second particle, both properties must have been predetermined all along. They must be elements of reality that quantum mechanics doesn't account for. Therefore, quantum mechanics must be incomplete, needing hidden variables to explain these perfect correlations. This presented a serious paradox. How could the second particle know what measurement was performed on the first particle and what result occurred without some signal passing between them? According to relativity, nothing can travel faster than light, yet the correlation seemed instantaneous. Einstein called this spooky action at a distance and refused to believe it could be true. The EPR team concluded that there must be a more complete theory waiting to be discovered, one that would restore locality and determinism to physics. Niels Bohr, quantum mechanics' foremost defender, responded to EPR in the same journal later that year. He argued that EPR had improperly applied the concepts of reality and locality. Bohr suggested that we shouldn't think of the two particles as separate entities once they've become entangled. Despite their spatial separation, they form a single quantum system. Measuring one part of an entangled system immediately affects the whole system. There's no distant influence to explain. Bohr also emphasized complementarity, that different measurements reveal complementary but mutually exclusive aspects of quantum reality. For Bohr, the EPR paradox wasn't a paradox at all, but reflected a deep limitation in how we classical humans intuitively understand reality. For decades, the EPR debate remained philosophical until physicist John Bell entered the scene in the 1960s. Bell devised a way to test whether Einstein's hidden variables could explain the quantum correlations. Bell's theorem showed that if local hidden variables existed, certain statistical correlations between measurements would satisfy what's now called Bell's inequality. But quantum mechanics predicted violations of this inequality. When experiments were finally conducted, most famously by Alain Aspect in the 1980s, they consistently showed violations of Bell's inequality. The results aligned with quantum mechanics, not with Einstein's local hidden variables. So what does this mean? The experimental violations of Bell's inequality suggest that nature really does behave in these spooky ways. Quantum entanglement is real, with particles maintaining instantaneous connections across space. But here's the crucial caveat. We still can't use entanglement to send information faster than light. While measurements are correlated, the specific outcomes are random until measured. Without controlling the outcomes, we can't encode messages to transmit superluminally. Today, we understand that quantum mechanics is complete in some profound sense, but it requires us to abandon either locality or what Einstein called realism, the idea that particles have definite properties before measurement. Far from being just a philosophical curiosity, the EPR paradox has spawned revolutionary technologies. Quantum computing, quantum cryptography, and quantum teleportation all leverage the eerie connections between entangled particles. The paradox that Einstein created to criticize quantum mechanics ended up validating its strangest predictions. What he called spooky has become the foundation of a coming quantum technological revolution. The EPR paradox takes us to the very edge of what is comprehensible. It reveals a universe where connections transcend space, where objects don't have definite properties until measured, and where reality seems to depend on our interactions with it. Einstein was ultimately wrong about quantum mechanics being incomplete, but his challenge strengthened the theory and deepened our understanding. Sometimes being wrong about the universe can be more productive than being right, if you ask the right questions. What the EPR paradox teaches us is that reality is far stranger than classical physics could have imagined. In our quest to understand the universe, we must be prepared to abandon our intuition and accept that nature might be fundamentally different from our everyday experience.